Okay, welcome to part 2 of the afternoon session. I'm your host, Ryan Thornton. I didn't realize that moderators were giving like little speeches, but I don't know, are there any questions? You'd like to ask me?
Well, you could sing or dance or something.
I don't think I'm going to sing or dance for you today, but okay, anyway. We're happy to have Meng Cheng here to tell us about global symmetry and anomalies and what was one DCFGs. Okay, first Meng.
Even works. Anyway, okay, so it's a pleasure to be here and thank the organizers for giving me this opportunity. So I'm going to talk about apparently a very old problem. So 1 plus 1 DCFT anomalies. This was certainly started in the 80s. Hopefully I can have something new to tell you. So this work was done in collaboration with our former postdoc, Dominic Williamson. Just moved to Stanford a couple weeks ago, so I'm not sure when the paper will appear. Okay, so we like to subscribe to these places of the phase space where you have fixed points on the RG. Of course, this is slide probably redundant for the audience. Conformal field theory is a quantum field theory with unitary quantum field theory with conformal symmetry, and these are fixed points under RG flow. If you have relativistic symmetry, and they show up a lot in condensed matter systems where you have emergent conformal symmetry. So we have a non-Lagrangian description for conformal field theory in terms of primary fields, operator product expansion, and some consistency conditions like crossing symmetry in general, or more powerful modular invariance, well, not sure more powerful, but modular invariance in 1 plus 1. So I'm going to focus on 1 plus 1, and as you all know, 1 plus 1, the conformal symmetry is enhanced significantly from just a conformal group to actually the infinite dimensional Virasoro algebra. So you can just mode expand the stress tensor, and these generators obey the Virasoro algebra with a C, the central charge. And what I'm writing here is a holomorphic or the chiral part of the theory, and there's a anti-holomorphic or anti-chiral part. So the whole symmetry is really the right moving Virasoro times the left moving one. And the Hilbert space of CFT, so once you have an algebra, the symmetry algebra, you can study the representations of the algebra, which gives, and then it gives you the Hilbert space of the theory. And the Hilbert space can be sort of schematically written as in this form, where you have this space for the chiral and anti-chiral part, and they are glued together in certain ways. So if we restrict to, say, unitary series and C is smaller than 1, then famously we get these minimum models. Discrete set of models parameterized by an integer greater than 3.
Are you assuming the CFT has a diagonal modular invariant?
I'll get to that.
Okay.
Wait.
Because you have H and H bar.
Yeah, well, in this case, I'm only talking about Virasoro, and in writing this equation, I'm assuming diagonal. Okay. But I'm going to relax it a little bit later. And we can have more symmetries, more than just the conformal symmetry. So, for example, the most well-known is there's some continuous symmetry, U1 or SUN, etc., and that gives you the Weston-Witten, well, for example, in Weston-Witten CFTs, and we can include the currents into the chiral algebra, and we get this extended chiral algebra, the fine Lie algebra. So this current just mode expansion of the actual current, and then they obey this kind of cut-smoothie algebra. Okay. So this is the most well-known extended current algebra, and there are also probably less familiar ones, more exotic ones. For example, W algebra for the W3 algebra in the three-state pulse model. So I'm going to assume that the left and the right current algebras are the same. And for most of the talk, I'm going to assume that the current algebra is maximally extended. So I include all the mutually commuting integer spin dimension fields into my current algebra. Okay. And we have these left movers and right movers. They have to be glued correctly to actually give a 1 plus 1 CFT. So this is a condition of modular invariance. So to formulate this, well, we can put a theory on a torus, which is parameterized by the complex parameter tau. And this is a character that sums over states in one of the conformal towers labeled by the highest weight representation of the chiral algebra, or the primary field A, the chiral primary field A. And then each of them transforms in a certain way under modular transformations. So if you change tau to tau plus 1, this is a T transformation, you pick up a face, and if you take tau to minus 1 over tau, that's an S transformation. And the total partitioning function on the torus takes this form, where M is an integer matrix, such that this combination is modular invariant. So that translates into a condition that M has to commute with S and T. Okay. For example, if we take M to be just delta AB, so we multiply tau bar of A with chi bar of A with chi of A, then this is a diagonal partitioning function, but you could have other choices, and we just refer them as non-diagonal partitioning functions. So the partitioning function determines, for example, a spectrum of a theory on a circle, or that's what we do usually in condensed matter systems. You put, say, your spin chain on a periodic boundary condition, and what operators actually appear in the spectrum is determined by the partitioning function. Okay, so and there was this beautiful theorem, the naturality theorem by Moore and Steinberg, that is, if the chiral algebra is actually maximally extended, so include everything that you can possibly include into the chiral algebra, then M has to take this form. So M is basically a permutation or automorphism of the Berliner algebra. So in the language that I'm used to now, it's just a permutation of topological chart labels of these chiral primaries A that preserves all the other properties, say the fusion rules and statistics. So I'm going to stick to maximally extended chiral algebra for most of the time, but we can relax it. Okay, so far just standard CFT, right? This is, say, the yellow book. And then we can, of course, consider global symmetries. So at this point, there are different ways you can think about it. For example, one can first figure out the largest emergent symmetry of the CFT, which is basically the chiral algebra, and then see how the symmetry you have microscopically embeds into that symmetry. But I'm going to just consider directly the global symmetry, which you can figure out from the lattice model or just from the UV. And let's say there's some global symmetry group G. And I'm going to assume that this is the internal symmetry for now. And it's a unitary symmetry, so like the simplest kind of symmetry that we can consider. And so we can ask, well, what the symmetry does to this CFT. Well, obviously the answer is that so the local scaling operators will transform as irreps of symmetry group G. Okay, I'm not claiming this is a classification, but this is how the symmetry should act in this theory. Okay. And this representation, if we just attach labels of irreps to different scaling fields, it has to be consistent with the data of the CFT, etc. So just for example, in the Ising model, obviously, Ising model has a Z2 symmetry, and the sigma field, which is all the parameter, transforms as a minus sign under Z2, and then the energy operator is even under symmetry. And another slightly more complicated example is the SU2 level K theory, the Weston-Witten model, where the primary fields are labeled by the spin 0 up to k over 2. And then, for example, one of the symmetry that this theory has is a center of SU2, which acts as -1 to 2j, so it puts a -1 to half all the integer fields and +1 to the other integer spin fields. And this symmetry turns out to be anomalous, which is quite a well-known result. So, so if we want to actually get a classification of these symmetry-enriched CFTs, then one has to be a lot more careful about equivalence conditions between these different assignments of representations. And as discussed in this recent paper, I think by Ryan and probably others in the audience, that one has to consider SPT sort of like edge modes. So I'm not going to talk about this at all. Okay, so the question I'm going to address is obvious from the title, that I'm going to consider how to compute the tooth anomaly in this CFT with global symmetry. And we have heard several talks on tooth anomaly, and this is something usually can be answered just based on very, well, not simple, but topological considerations. Okay. So we know that in the bosonic system, and the dimension that we are in right now is 1 + 1, so anomaly is classified by a third cohomology group, which is also the classification of symmetry protected faces in 2 + 1, is characterized by a cocycle, 3 cocycle in H of 3, with a U1 coefficient. Okay, so how do I compute a tooth anomaly in a 1 + 1 theory? Well, the most general prescription is probably just introducing symmetry defects, and in this particular context, they are called topological defect lines and labeled by the group elements. And then if you look at the associativity of these defect lines when they fuse, you can read off this phase vector. Okay, so this is probably the most general prescription that one can come up with. And well, I'm not sure this is a complete reference, but this is what I know. But this is a little too general for me, but I want something a little more concrete. And another approach to the computation of tooth anomaly is to look at orbifold partition function. Right? So you put a theory on the torus and introducing twists, symmetry twists in two directions, and see whether you can make the partition function modular invariant. So this was, of course, also started in the 80s, and then here are more recent references which apply this idea to the study of H series of SPT faces. Well, this has a little problem, that is, sometimes the torus partition function, the S and T modular transformations are not enough to fully determine the anomaly, which was Shieda's talk, although it doesn't really show up for small groups. So what I want, so this is what I'm going to talk about, is that I want some kind of anomaly, something like an anomaly indicator that goes directly from this data, so how the local fields, local scaling operators transform under G directly to a 3 cocycle. So this is my goal. I want to have a formula that just takes me from this data to the 3 cocycle. Okay, so how do I do this? Well, how should I proceed? Well, so for 1 + 1 CFT, there's an extremely powerful tool that we can use that is a bulk boundary correspondence, and we really understand a lot about the topological field theory in 2 + 1. So rational conformal field theory and MTCs are, it's well known that they are closely related. So I forgot to say that everything is rational, only have finite number of private fields. And well, there are a few ways to state the correspondence. One is that the TQFT Hilbert space on the Riemann surface are given by the conformal blocks of the chiral CFT. For condensed matter series, probably a better picture is the following. So let's say we have a 2 + 1 chiral topological face on a disk, and then there's an edge which has this chiral CFT running on it. So we can create a pair of quasi-particles in the bulk, these are anyons, and take one of them to the boundary, and that's the chiral primary of the rational CFT on the boundary. Or we can we can take this pair of anyons and then put both of them on the boundary, and then that leaves nothing in the bulk, so that's sort of like a non-local string operator on the boundary. Okay. So the bottom line is that there's this one-to-one correspondence between anyons in this bulk 2D topological face with the chiral primaries of the rational CFT. Okay. But this is just one half of a true 1 + 1 CFT. So to get the other half, well, you need another copy of the bulk, or I can just sort of fold this bulk into folding it so that I can expose really the chiral and both chiral and anti-chiral parts on one side of the edge, and this is a full CFT. So another way of saying the same thing, that I take two copies, one, well, really not two identical copies, one is a conjugate of the other, but I gap out the other side, and I'm left with a full CFT on one side. Okay. So this is sort of a kind of a useful model for 1 + 1D CFT to get a full non-chiral CFT. So this is about correspondence. That is, I can take this sort of two-layer bulk topological face, which is some modular tensor category described by some modular tensor category B and its conjugate, and then I gap out one edge, so I'm left with the other edge, which is now a 1 + 1 theory. Okay, so I can draw the picture slightly differently, so that this looks like a strip of 2 + 1 topological face. So this is now looking like a dimension reduction picture that I take a 2D system and I compactify it on a strip, and then I get a 1 + 1 theory. Okay. So I have a top and bottom edge which have counterpropagating chiral degree of freedom. Okay, so this picture is kind of useful because I can make very precise the relation between the local operators in CFT with what I have in the bulk. So there are two kinds of local operators that appear in this strip. So one type are the local operators that are already present on one edge. So even on one chiral edge, I have some local operators. Well, these are basically the chiral algebra. Whatever you have in the chiral algebra, these are local operators that are already present on one chiral edge. Okay, but that's not the whole story, because now, because I treat this strip as a 1D system, I could tunnel an anion from the top edge to the bottom edge. So these are the primary fields, basically, of the 1 + 1 CFT. That is, that we can view it as a tunneling operator from top to the bottom. Okay. But on top of all these, I could insert a defect line in the middle. This could be invertible or non-invertible. In the case of maximally extended chiral algebra, this must be an invertible line, so it's a symmetry defect line, basically. So this picture was advanced in, again, I'm not sure this is a complete list of references, but in this paper by Fox and also by Anton.
7 minutes. 7 minutes.
Oh, okay. I'm getting there. So, all right. So to derive an anomaly formula, well, we want to make this CFT actually appearing on the edge of SPT. So what I'm going to do is basically I'm going to sticking a layer of SPT phase, which has that H of 3 per cycle, to this folded layers, such that this boundary is symmetric and gapped. So if this is the case, it means that the CFT on the other side of the folded layers can appear as edge theory of the SPT, preserving all the symmetries, etc. So this is equivalent to the existence of a symmetric gap boundary between these folded SET layers with symmetric protection phase here. So, well, we have learned a lot more about symmetry enriched topological phase in the past several years, so I'm not going to get into all the details. But just to quickly mention the data that characterize the symmetry enriched phase in 2 + 1. So again, there are, well, no, we can eventually nail it down to three pieces of data. One is how the symmetry permutes topological charges in the topological order, and then symmetry can fractionalize on anions, and then on top of that you can stack SPT. Okay. And then there are some obstruction classes. So this more or less gives you a classification of 2D SET phases. I'm going to, well, just for the sake of time, I have to skip this, but not the last comments. So I'm going to use this W to denote the symmetry fractionalization class. That's basically how anions individually transform under symmetry projectively. And then there's H of 3 that characterize SPT you stack on top of your SCT. So different choices of this row, the permutation, and also the fractionalization class correspond to distinct bulk phases up to some equivalence under row, basically. But then a sort of well-known subtlety is that if you choose different alpha, different SPT stacked on the SCT, that may actually give you the same bulk. Okay, so, but this is exactly the same problem that we just mentioned. So if you stack SPT on top of a SCT phase, and we ask the question whether this is actually a new distinct phase or not, well, since SPT really just changes the boundary physics, so this boils down to the question whether there's an invertible symmetric interface between this SCT and this is SCT, but with one additional layer of SPT. Okay, but then you can fold this whole thing, fold the SCT over to the other side, conjugate this layer, and then you get this picture. So basically, these are the same questions. So we have to study the gap boundary between this double layer of SCT and then the SPT. And also, by now, we have enough machinery already in the mathematical literature to study this problem. So let me go through this quickly. So on this boundary, well, the gap boundary of this double layer can be described by what anyons condense on the boundary. On the other hand, what it really says is you can take one particle on the top layer and then turn it to an anyon on the bottom layer. So that's a gap boundary. And if the gap boundary sort of just the particle goes into the same particle, then it's a diagonal partition function if you view it as a CFT. And if undergoes some permutation, then it's a non-diagonal CFT. Okay. So we can impose some conditions to make sure that this boundary is symmetric. So I have to skip all the derivations. But in the end of the day, there appears another piece of data that characterizes the symmetry property of the gap boundary. Basically, even though the anyons condensed on this boundary cannot transform projectively under symmetry, but it can still transform as a one-dimensional representation. So it can carry charge under a symmetry, and that's characterized by a map from the group to the group of abelian anyons. Okay. So that's another piece of data that we need to describe this setup. Okay, so in the CFT interpretation, so we have two pieces of data from the bulk. One is the fractionalization class of the bulk system, and the other one is this additional piece of data that describes this gap boundary, what anyon, what charge is carried by this condensed anyon. And together, they exactly correspond to the two types of local operators. So this fractionalization class basically determine what symmetry representations are carried by the chiral algebra on one edge alone. And then this additional piece of data tells you how these primary fields, which are represented as the tunneling operator of anyons from one edge to another, transform under the symmetry as a one-dimensional rep. So once you have these two pieces of data, then we can write down a formula for anomaly. So again, I skip all derivations. So this is not complete general, but in the case of trivial fractionalization class, or in the CFT language, when the symmetry actually commutes with the whole chiral algebra, there's just a simple formula for the 3 cocycle in terms of the F symbol of these anyons. And then in this case, I can actually have a complete general permutation on this invertible defect line, which means I could have non-diagonal partition function. So in the other case where I could have, I allow general fractionalization class, then what I can do is assuming a diagonal partition function, then I can get this 3 cocycle in terms of the same F, but we have another factor here that's written in terms of a braiding between the W and V. Okay. All right, so let me just make one remark here that, so this is the same kind of data that we have in the CFT that is just determines how local operators transform under the symmetry, but from this bulk boundary correspondence, so I'm breaking it into these two pieces of data. It's completely equivalent, there's nothing new here, but it's just different way of representing the same set of information. Okay, so am I already?
I have 1 minute.
Okay, that's enough for the last 2 slides. So All right, so of course, let's look at minimum models. So minimum models, basically, the Chiral algebra is just a Virasoro algebra, so no extended Chiral algebra. And because any symmetry in the QFT should commute with a stress tensor, so the symmetry should commute with Chiral algebra. So that means there cannot be any fractionalization class from the bulk point of view. And that simplifies the calculation a lot, and then you can just look at the data of this CFT, and then the conclusion is that, well, in this particular case, if the symmetry actually commutes with the whole Virasoro algebra, which is very natural for minimum models, then the minimum model cannot have any two anomaly. Okay? It just doesn't have enough symmetries to do that. Now, one subtlety here is that some minimum models, you can further extend the Chiral algebra. For example, for the M5, 4, you can put a spin 3 particle, well, spin 3 operator in the Chiral algebra, and you get Z3 parafermion. So you can deal with this kind of minimum models with extended algebra, and then you get the same results, okay? Although with a little more work. And we can also compute anomaly for SU2 level K, and SU3 level K. So for SU2 level K, the abelian anyons just form a very simple Z2 group. And then we can just compute anomaly in general. We get this formula. Everything's written additively. So in the case that symmetry commutes with the Chiral algebra, then we recover the well-known result. That is, for Z2 symmetry, the odd level has a anomaly. It has a two-fold anomaly, but the even ones don't. Okay. We can do the same computation for SU3 level K, for example. I mean, you can do it for SUN level K. But for SU any odd level K, if the n here is odd, so for example SU3, then it turns out that if the symmetry commutes with the Chiral algebra, then there's no anomaly at all. So this can be generalized to any other SUN level K with odd n. Okay, so this is my summary slides, and I think hopefully I'm on time. Right, thank you very much for attention.
Can you scroll one slide back?
Okay.
So here, so let's talk about the SU2 example.
Right.
K is 2 mod 4. We would say there's no anomaly, which means we can gauge it, but when you gauge it, it's different than when K is 0 mod 4.
Okay.
So
Yeah.
does your formalism see this distinction?
For K2 mod 4, well, then the highest spin particle is a fermion, right? So that's, I guess, the only
For 0
difference.
mod 4, you really extend the chiral algebra. For the 2 mod 4, you do not.
Yeah, so for 0 mod 4, I can further extend the Chiral algebra, and for 2 mod 4, I cannot.
But can you detect it from this anomaly?
I don't really see this from this particular Z2 anomaly. It doesn't further distinguish a case of K2 mod 4, 0 mod 4. So it just only cares about even odd K.
Now, even when K is odd, you can still gauge it and get the theory which depends on spin structure.
Okay, odd, highest spin particle has spin a quarter. I'm not sure why it's a spin structure.
Well, you can extend the chiral algebra with a fermionic theory. It's like the Ising model, which has fermions, but no.
For odd K? Is that?
You mean 2 mod 4.
2 mod 4, you mean 2 mod 4, when K is 2 mod 4. For odd K, there's no spin.
Take it back, yeah. Thank you. So the other question is, the old-fashioned way of addressing that was just trying to construct the overfold
Right.
and making sure that you have locality
Right.
plane and modular invariance.
Right.
Does this give anything that is not given to the other?
So I think that goes back to the same question whether it's enough to do it on torus. So if you do it on any homogeneous manifold and maybe in some punctured spheres with enough punctures, you construct continuous functions, and I think that's enough. But if you only do it on torus by looking at characters, in principle, right, there are exceptions, well, counterexamples where S and T do not determine the H of 3.
Yeah, but the old argument, which is the same thing as the previous talk, endpoint function, I think it's enough to check locality of the 4-point function, maybe you should go to 5. And 1 point on the torus, this is enough to guarantee consistency of all homogeneous.
Right, so when I say the orbifold, I guess I only mean a torus without any puncture and looking at the combination of characters to whether you can form a symmetric orbifold or a modular invariant orbifold. So it's always true that if there's an anomaly, the modular invariance cannot be, you cannot have modular invariance, it must break down. But whether you can recover the HR3 or not, just from the torus partition function, not including these ones with punctures, that's not always the case.
Maybe we should move this discussion to after the talks and take one more quick question.
Yeah.
So your derivation, I guess, only applies to irrational CFTs.
Rational safety
Does
only.
your answer work for irrational CFTs?
I don't know any irrational CFTs, except the U1 boson.
Not the sigma.
Sorry, I have to learn that first to answer your question. Yeah, I don't know any irrational CFTs in condensed matter literature. Except bosons compactify on irrational radius, and there's some candidate of like coupling 3 possible together, but other than that, I don't know. All right.
Great, let's thank Meng again.